Sure, you've seen an object like this before. It's a big heavy weight bouncing on the bottom of a spring. Perhaps you've seen that old Scooby-Doo cartoon where the guy tries to hypnotize you by hanging a watch on the end of a swing and on the end of a string, and swinging it back and forth in front of you. Well, these are both examples of something that we'll call simple harmonic motion. And this little just-in-time lecture today is about simple harmonic motion and Hooke's law. Periodic motion is what we were just looking at, actually. Periodic motion is any sort of a motion that is repeatable, regular, oftentimes a swinging motion, but not necessarily swinging. I mean, there's other things that can be periodic as well. The examples I've got in there, a kid swinging back and forth on a swing, the pendulum of a grandfather clock slowly going back and forth, an actual pendulum, like I said, something like you're hanging up and up, down, swinging back and forth, something like this weight on a spring, bouncing up and down, or perhaps if you've ever gone bungee jumping before when you're bouncing at the end of the rope, or this thing up at the top right corner that you can see, a metronome is another example of a type of periodic motion. You could also say me coming to work every day is an example of periodic motion, or maybe the way the sun comes up every day is an example of periodic motion. Simple, repetitive motion. So as objects go through these types of periodic motions, we can say some things about characterize its motion. So for example, we know that the velocity, the acceleration of that object are going to change in really regular and periodic ways, and furthermore that the force that object is experiencing is also being repeated in a very regular way. So think about that little kid on the swing, here he is. Doesn't she look happy? So for this particular example, imagine that the child's young enough that they're not actually kicking the legs or helping out. So dad pulls the kid way up and then just lets her go. We used to love doing that with Sierra. So at the beginning of that arc, when the kid's way back high, right, we can call that maximum displacement. The kid's as far away from kind of the normal hanging position as possible. And at that particular instant, when you let the child go, of course the child's going to experience maximum acceleration. Why? Because that's where they're the highest. They've got the most potential energy, gravitational potential energy in this case, and so therefore they're going to experience the most force as well, F equals ma. At the bottom of the arc, when they get to the middle of that swing, they're going to be experiencing that maximum velocity, woohoo, right, as you go through the bottom of the swing. That position at the bottom, when you're experiencing maximum velocity, is called the equilibrium position. And don't forget, at the equilibrium position, you're also experiencing zero acceleration. It's actually changing, or you're actually sort of decelerating, I guess, if you want to think of it that way. Now, as the child continues through the swing and goes up the other side, you're also experiencing, at the other end, maximum acceleration, now in the opposite direction, and maximum force as well, but now kind of backwards, right? So just in the opposite direction. This is that example of periodic motion. That cycle will repeat itself over and over and over again, obviously without air resistance. You go from maximum positive displacement through the equilibrium position to maximum negative displacement, and then back through equilibrium again. By the way, at the bottom, that loss of swing or the loss of bounce in my little spring example, it's called dampening. And those are things that happen due to friction, internal friction, air resistance, things like that. So we're going to use kind of our spherical chicken assumptions and pretend like that's not really going to happen in our systems. So we have to make a little bit of a distinction here. The movement back and forth of this child on the swing is not only periodic motion, but we can also characterize this as being simple harmonic motion. So simple harmonic motion is simply a type of periodic motion, but it's being caused by, and this is the key word, a restoring force. Some force is pulling that object back towards center, and then it kind of goes past, and then comes back to center. Or when we're talking about our lovely weight on the spring, you know, when it's down here, and then it comes up to kind of equilibrium, and then bounces up, and then comes back down. That's simple harmonic motion. There's some sort of a force restoring it to that original equilibrium kind of central position. The further an object gets from that equilibrium point, the greater the experience of that force is going to be. So for the spring example is a really good one. As it gets further down, as it's pulling all the way to the bottom of that spring travel, it's really going to want to pop back up. Or as that child on the swing gets further up towards the top, it's going to really experience that force, that acceleration, back down towards equilibrium. And again, on the swing, that force is gravity. Same thing with our spring example here, because the spring is hanging down, gravity is the force that it's causing this. I want to take a quick moment here and sort of distinguish quickly between periodic motion and simple harmonic motion. Anything that's regular repeating motion is periodic. All three pictures on this page are examples of periodic motion. So appearance of a comet in the sky, or perhaps the moon or the sun in the sky, are all types of periodic motion. A sine wave, when you do a sine graph like that, is an example of periodic motion. And even a hula hoop, something going in circular motion. Those are periodic, but they're not actually harmonic motion because there's no true restoring force that's pulling back them to some sort of an equilibrium position. Simple harmonic motion's always back and forth, either left to center to right to center, or up to center to down to center, something along those lines. That's always going to be harmonic motion. We talk about harmonic motion simply because it's the easiest one to mathematically kind of talk about. Periodic motion can get much more complicated. So when we're trying to give a good example of harmonic motion, a lot of times we're going to do springs. This is what we're doing in the labs. You're going to be doing a Hooke's Law lab as well that kind of explores this relationship. But you know a lot about how this works. So for example, we know that there's a relationship between force and displacement. The amount that a spring is going to stretch is dependent upon the amount of force or weight that's being hung upon that spring. So if I hang, in this first example right here, this one, if I hang some sort of an object on a spring, it's going to displace a certain amount, and they call it X in this particular picture. Why? The force that's displacing it is the force of gravity. So if I hang something that's twice as heavy, in this picture over here on the right, I know that it's going to displace twice as much. There's a definite relationship between how far something moves and how much force is being applied, or vice versa. How much force is being applied is going to affect how far something moves. And again, you can turn this picture upside down. We can also talk about compressing springs. A spring like this is already compressed, so it doesn't really compress anymore. But this one that's up in the picture up here is like a coil spring from a car. On this one, you could actually apply mass to it to compress it, squish it down. And that's a different kind of displacement. It would be mathematically the same, a different negative sign, as opposed to stretching a spring out. So either one of those works. This particular relationship is called Hooke's Law. And Hooke's Law is a mathematical little simple equation. There it is. But it's the relationship. It states that the extension or displacement of a spring, or the compression of a spring as well, is directly proportional to how much force is being applied to it. Or vice versa, the amount of force that's being applied to it will be directly proportional to how much that spring is being expanded or compressed. How much is directly related to this thing called the spring constant. Spring constant is simply a number. It's called K, but it's simply a number that talks about how stiff the spring is. So, this little spring like this one that's pretty easy to pull, it's going to have a pretty small K value. This giant suspension spring in this truck over here is going to have a huge K value. It's very difficult to compress that. And again, so it relates to the amount of force. And just at the bottom, I just wanted to remind you again, we've seen something like this before when we did the unit on energy, and that when we look at the equation for potential energy, elastic potential energy, very similar format. It's the same kind of idea where it's the energy in a spring is related to the displacement squared now times that spring constant. Again, just a little bit different. So force, potential energy, they're definitely closely related concepts. So, last couple things here. Why does this equation have a negative sign? And students kind of ask me this regularly. Why is that there? Why isn't just F equals KX? And the important thing to realize here is that the way that you're displacing the spring and the force in the spring are always opposite directions. So if I am displacing the spring this way, the force of the spring is obviously pulling it back towards the center. So when I let go, it's going to snap that way. So because they're in opposite directions, we have to use a negative sign in there. Same thing if we're actually trying to compress the spring, then the spring is going to be fighting back by pushing away on the other ones. And then the last little trick, and we're done. Remember that if you're trying to figure out what F elastic is, if a problem is trying to have you calculate Fe, and you don't know what that is, if you've got an object hanging on a spring like this, the elastic force, remember this thing is at equilibrium, that means that this force has to be equal and opposite to this force. In other words, Fg is equal and opposite to Fe. And you can use that in any of your math problems. There you go. Thanks. See you in class.